s-SNOM. So I'm very happy to own one. How does this work? Yeah, I think I just used the keyboard. Okay, so the title, I modified the title a little bit, called it Optical Skyrmion, a new texture of light. And the reason I used the word texture is that magnetism people often use this term in order to describe the orientation of the magnetic moments or magnetic spins. So I thought it would be a good idea that will fit the general concept. I would also like to thank the previous speaker who saved me some of the introduction, because I'm also using transmission mode, but in a different way, which I will elaborate a little. But just a little, because I was asked to talk mostly about the skyrmions and less about the measurement. Okay, so texture, so the text now is all totally corrupt. Okay, so anyway, textures in physics in general, it's in simple words, it's about how some vector field, usually real, is oriented along or in a space, or oriented different places in a space, and the laser. And examples we can find like spin textures, find them in cold atoms, also in topological insulator, or the orientation of molecules in liquid crystals. But, ouch, most famously, texture is used to describe the orientation of the magnetic spin or magnetic moments, and by this to characterize them. So, for example, if there is the moments they're not oriented, if the moments are random, then this makes a paramagnet. If they're all aligned along the same direction, that will be a ferromagnet. If they align opposite direction for the neighboring, then it will be anti-ferromagnet, and so on and so forth. But there is another ordered texture to magnets, or to magnetic material, which is not either a ferromagnet or anti-ferromagnet, and these are the skyrmions that I want to talk about. But before, yeah, let's say skyrmions. Okay. But before I start talking about skyrmions and magnets, just a brief history. What are skyrmions and how did they start? Why are they named skyrmion? They're named skyrmion after the guy who conceived them, which is Tony Skyrm, which was almost 60 years ago at a totally different field. It actually was a high-energy physicist, and he was looking for a way to make the energetic particles more stable, because we know that energetic particles decay very, very fast. Because they're so energetic. And what he found, and this is stated here in this paper, that if you arrange them at a certain way, or distribute the orientation of the field vector in space, then they can become more stable. So how exactly did he propose to arrange them? Or actually what he found is that what will make them more robust or more stable, that if you arrange them in such a way that will span all the direction within a unit cell, if it's periodic structure, or within the entire space, if the boundary conditions are at infinity. How can we describe it in a simple way? So consider a hedgehog, or actually consider a spherical hedgehog. So he has the pines pointing at all directions, right? Because they are normal to a sphere. And now we crush this hedgehog into a plane, or in other words, we perform the coordinate transformation, mapping a sphere to a space. So the northern pole is mapped to the center, the southern pole is mapped to infinity, and in between, we have all the different orientation, right? So we go from spin up, gradually to spin down, and in all 2 pi angles, so along the space, or across the space, or across the unit cell, if it's periodic boundary conditions, then the vectors span, or the vectors, these pines, point at all directions. There's a different configuration which also works, and this is called the combed hedgehogs. That you took a hedgehog and you combed these pines, and it also spans all possible direction, but a different way. Instead of spanning it like this, it's spanning it like that. Okay, but it also does the work, and there is also the degenerate condition at the boundary, because there is another property. It's not just if they do or they span all the direction, or how abrupt is the change from the spin up or the spin down. So it could be gradual, or it could be at the extremes that it's up, 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 down, and then stays down. Okay, so this extreme state, which degenerates the two other types is actually a bubble, is what we know as a magnetic bubble, and this area where the change occurs abruptly is what is called the domain walls of the magnetic bubble, and oh, that's written okay. So these are called nail-type skyrmions, these are called block-type skyrmion, and this is the magnetic bubble which degenerates the two of them. So what is interesting in the skyrmion, and actually what makes it robust, that they have kind of topological protection. So in other words, they are a topological state. They can be identified by a topological invariant called the skyrmion number or the Pontryagin index. I will not get now into the details how to calculate it, but what it does, it quantifies how many times the entire space of directions was spun. Okay, so if S equal 1, it means that within one unit cell, or infinity with infinite boundary condition, all the directions are pointed once. If skyrmion number is 5, then within this defined area, all these directions are pointed 5 times, and so on and so forth. So that's a skyrmion number. It's analytical, so it can be calculated analytically. Okay, what is important to say, which may be trivial for all this system, but not for what I'm going to talk about, is that this is a real vector field, right? This spin is a real vector field, and it also have to be non-vanishing because it's a normalized field, so we cannot allow any points that it will be 0 in all directions, and the proper boundary conditions have to be defined. Usually it's either at infinity or the periodic boundary conditions. So since this discovery, the skyrmion have been found in the different systems, whereas the most exciting of them is in chiral magnets, for several reasons. First, you can see it's very aesthetic. I mean, this is very beautiful pictures shown or taken in transmission electron microscope. So this is the out-of-plane magnetization. This is the in-plane that looks like a nice vortex array, but it's not the vortex as the optical vortex as we know it. But I guess the big impact that they are supposed to do is because they aim to do to form the next generation of magnetic memories that will be robust because of the topological protection, and also high capacity because this feature can be very small and then can be mobile. So in other words, these skyrmions aim to make magnetic memories great again. Now, all of this is about magnetics, but we're talking about electromagnetics or optics. And for doing skyrmions in optics or in electromagnetic field, we first need to motivate it or to understand why do we want to do it. Okay, so the real answer is we do it for fun, but that's what we all do. But we do need sometimes to justify it, and there are actually some good reasons to motivate this work. So skyrmions, typically in magnets, they form spontaneously as a phase transition, and they're not always controllable. They are, of course, in low temperature usually, and here we can get skyrmions on demand. If we can do it, we can do them with light or with the electromagnetic waves, so we can control their properties, and of course in room temperature, and then we can use light-matter interaction in order to induce them in other systems that they may be beneficial there. Okay, and also we have some fundamental scientific bonus that in optical system there are some nonlinearities, and then we can play with nonlinearities and find some new physics and so on and so forth. And I also must say, although I cannot justify it, that following the motivation of magnetic skyrmion for data storage and processing, well, maybe we can use them if it would be successful for optical information processing and storage. But again, I cannot justify this claim right now. Namely, I don't know, I cannot tell you how we can do that. There are also some limitations. Actually, there are some problems. Actually, I had a different slide for this. So there are actually two main problems. One of them is that the magnetic system and the optical system are totally different. Namely, the solutions are not necessarily the same because the magnetic, they have some kind of Hamiltonian, some nonlinear complicated Hamiltonian, and that's the solution of it there are these skyrmions. And in electromagnetics, we have Maxwell equations, or the wave equation, which is very different Hamiltonian. So this is one thing. The other thing is about being real versus being complex. So electromagnetic fields or the phase of electromagnetic fields, it can be complex. So it can have a phase that changes with place. It can have relative phase between different components of the vector, which is not allowed in real wave vectors. So we have to solve this. Again, I won't go through all the details, but we can solve it. In particular, we can find a specific solution, which is this solution. This is the field solution. I will not go to details how we found it. I have some very nice stories about it, but we don't have time for it. Eventually, we can come up with this kind of solution. So this is a vector field. It's evanescent. As you can see in Z, it's e to the minus kz. It has to be evanescent. Otherwise, it will not work. 3 minutes, really. Didn't get to the interesting part yet. Anyway, and it's real. Okay, so you can take it for me, and this is how it looks. So this is the out-of-plane field. This is the in-plane, the amplitude of the magnitude of the in-plane, and these are the direction of the in-plane. As you can see, it points in all directions, and if we plot the entire field, the entire 3-vector field, we find out that indeed within each of the unit cells, it points in all directions, and we can calculate the number and get a Skyrmion number equal 1. So far for the theory. Now we have to know how to generate them, and in this forum I can entangle the measurement, not entangle in the quantum means, but I can combine the measurement also with the generation also with the measurement. So we also use transmission mode, but we use it in a different way without the synchronization. We carve some arbitrary coupling grating, typically illuminated with circular polarization. We have some reasons for it. And we use a very broad beam, such that, and this is how we don't get the phase and amplitude distortion. We have just used a beam that is broader than the range of the motion. Okay, so you know the technique, so I don't need to elaborate it too much. What I mentioned before that it's very important to have the evanescent waves in order for this solution to work, but it doesn't matter how we get this evanescent wave. As far as I'm concerned, it can be total return reflection, it can be guided wave, and of course it can be surface plasmon, and we choose surface plasmon mostly because it is very compatible with the methods that we use because they already provide the mask because they're opaque, right? So we just need to carve the slits or the coupling slits and use our method, and we are good on it. So this is how the slits look. But that can be quite confusing because it looks very simple. Well, it is a hexagon, but the hexagon, it will generate interference pattern of these 6 beams. We illuminate with circular polarization, so there is some inherent phase delay between the slits, which is good for us. But what is interesting here is that it gives us some degrees of freedom, and in fact, it can generate 4 different topologies. When I mean topologies, I'm talking about topological charge of the vortices that created by the lattice. Okay, and the way we can switch between them is by playing with the boundary conditions. Boundary conditions means we can shift one or more of these coupling slits. It adds some relative phase between them, and it does totally different effect, which is quite surprising if you did not know that ahead. Another important thing that I want to say regarding the measurement, I mean, the measurement, you can consider it as trivial. We use really the old model, the first generation, but the pseudo-heterodyne measurement, it gives us the wonderful properties that we have the full information of the electromagnetic field, amplitude and phase, as a function of x and y. So even that we measure only a single component, the out-of-plane component, by knowing all the information, we can extract also the in-plane component. Another very important thing that it does, it allows us to perform a spatial Fourier transform. So for the spatial Fourier transform, we gain more information. For example, exactly what is the in-plane wave vector, or the effective index, or the mode index that the previous speaker mentioned. And it also allows us to efficiently filter noise and background. Okay, so let's go. So this is how we extract the in-plane field. And these are the experimental results of the 1, 2, 3, 4 different. So they look the same, but they have different boundary conditions. And you see they generate totally different patterns, totally different topologies. So if we go fast, these are experimental. So this is amplitude and phase. So without any change in the hexagon, because of the circular polarization, we get an array of a vortex. This is, you can see it very nicely, the phase. This is order 2, so we have here order 2, and it's a Kagome lattice. This is order 3, but it's not really a vortex because it's just 0 pi, 0 pi, 0 pi. The thing is that none of them can make a skyrmion because they have phase structure, which we cannot allow, and they also have singularity. The one that can make skyrmions is actually the 0 topology, which we can also generate it with proper boundary condition. So this is amplitude and phase. From this, we extract the field, which is real, up to some losses and imperfection. Fourier plan, this is the Fourier plan of it. Filter the noise, and also extract what is the in-plane wave vector. And from this, we can extract the in-plane field, amplitude, direction, and this is a 3D plot of the experimental results, which were mentioned. So this provides the demonstration of the electromagnetic or optical skyrmions. We can do all kinds of quantification. For example, these are the domain wall. These are the areas where the changes occur at the most abrupt way. And I have quite a lot more to say, but I guess I ran out of time. So if you want to ask questions about all these photos, you are welcome. And I will just jump to acknowledging the teams that worked on this. So this is the Shai Tzesses, the student who was the main driver of the work. Kobe and Evgeny were the experts on the tool, on the s-SNOM. Bergin, former postdoc, and Professor Nathaniel Linder from the physics department in our institute to provide the theoretical backbone, helped us with the theoretical backbone of this work. And with this, I'd like to thank you for your attention.